They banned it, then copied it, then made it the standard. And it all started with a single question nobody else thought to ask. What if we just let the air out? Here's the thing about drag racing in the early 1980s. Every single team, every crew chief, every tire engineer worth their salt agreed on one thing. You do not drop your rear tire pressure below 6 PSI. That was the floor. The absolute bottom. Go lower and your tire blows off the rim, your car snaps sideways at 180 miles per hour, and you become a very expensive fireball in front of a very large crowd. This wasn't a suggestion. It wasn't a guideline. It was gospel, carved in stone, written in the blood of racers who'd learned the hard way. And then Lee Shepard showed up with 4 PSI and beat everybody. Not once. Not twice. He was virtually untouchable for 2 full seasons. His 60-foot times were so absurd, so far outside of what anyone thought was physically possible, that officials tore his car apart looking for hidden technology. They found nothing illegal. No traction control, no exotic compounds, no secret witchcraft buried in the chassis. Just a set of tires that looked like they were melting into the asphalt and a crew chief who kept a precision-calibrated gauge in his back pocket like a loaded weapon. This is legacy motoring, and I spend way too much time thinking about the moments in motorsport history where one person figured out something so blindingly obvious that the entire sport felt embarrassed for missing it. If you're someone who loves the deep technical stories behind racing legends, the stuff that never makes the highlight reels but actually decided championships, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, you might be thinking, okay, tire pressure, sure, interesting, but is this really a revolution? Is this actually worth 40 minutes of my life? Let me give you a number. Before Lee Shepard's innovation took hold across the pro stock field, the benchmark 60-foot time, the gold standard that separated good racers from great ones, sat around 1.05 seconds. After 4 PSI became the standard operating procedure, that number dropped to 0.90 seconds. That is a 15% improvement. From tire pressure alone. No engine development. No weight reduction. No aerodynamic breakthroughs. 15%. In a class where races were decided by thousandths of a second, where a team might spend $200,000 chasing 200ths of improvement, 15% from simply releasing air is the kind of number that makes grown engineers question their entire careers. But to really understand why this was so seismic, why it shook pro stock to its foundation and eventually rippled across every form of motorsport on the planet, we need to go back. Back to what pro stock actually was in 1983, and why it was the most brutally competitive, technically demanding, unforgiving racing class in America. Pro stock was the ultimate door slammer category. These cars looked like production vehicles. Camaros, Thunderbirds, Oldsmobiles. But underneath those familiar body panels, they shared almost nothing with anything you could drive off a showroom floor. We're talking 500 cubic inch, naturally aspirated monsters making over 900 horsepower. No superchargers. No nitrous oxide. No turbos. Just raw, screaming American displacement pushed to the absolute mechanical limit through carburetors and mechanical fuel injection systems hand-built by people who treated engine assembly the way surgeons treat open-heart operations. The competition roster reads like a Hall of Fame. Bob Glidden, perhaps the most technically gifted racer of his era, was running a Ford Thunderbird program backed by serious factory support. Warren Johnson, who earned the nickname the Professor because he genuinely approached racing the way an aerospace engineer approaches telemetry data, was analyzing every variable with a level of obsessive precision that made other racers uncomfortable. Wally Booth, Butch Leal, Frank Iaconio. These weren't weekend hobbyists. These were full-time professional racing operations with million-dollar annual budgets and dedicated engineering staff. These were people who ate, breathed, and occasionally wept over horsepower numbers. And yet, for all the sophistication, For all the technology and the money and the combined brain power pointed at going faster, the entire class was stuck on the same stubborn problem: the 60-foot time. Here's what most people don't realize about drag racing physics. The first 60 feet of a quarter-mile run is where championships are actually decided. It sounds counterintuitive because the finish line is 1,320 feet away, but the data is unambiguous. A single tenth of a second advantage at 60 feet translates to roughly 3/10 at the finish line. In pro stock, where the entire competitive field is typically separated by less than 2/10 total, a 3/10 swing is not an advantage. It's a demolition. It's the difference between low qualifier and first-round loser sitting in the trailer at lunch wondering what went wrong. And the 60-foot time lives or dies on one thing: traction. How much of your power you can actually transfer to the asphalt versus how much you're just spinning away in a cloud of tire smoke and frustration. This is where it gets really interesting because everyone understood this. The entire field understood that traction at launch was the crucial variable. And the entire field had collectively agreed, through years of testing and bitter experience and the occasional spectacular tire failure, that the optimal rear tire pressure was between 8 and 10 psi. That range gave you the best balance between contact patch size and sidewall stability. It gave your tire enough structure to handle the violent torque impulse of a 500 cubic inch engine spinning up to 7,000 RPM at the hit. Go lower than 6 and you were gambling with your life. This consensus wasn't arbitrary. It was built on real data and real consequences. The bias-ply tires of the previous decade genuinely could not hold their bead below certain pressures. The technology had a hard floor, and the floor was 6 psi. Experienced crew chiefs had watched tires come apart catastrophically below that threshold. The institutional memory of the paddock said 6 psi is where you die, and nobody argued. Nobody except a Florida racer who'd started his career on motorcycles and never quite absorbed the memo about what was impossible. Lee Shepard was not a household name in 1982. He was competitive, talented, running a Camaro program out of Florida without the factory backing or the engineering depth of a Glidden or Johnson operation. What he had, and this is the part that matters, was a mind that refused to treat conventional wisdom as settled fact. He asked questions that polite company had stopped asking. He followed data past the point where most people got nervous and turned back. And in early 1983, during a test session at Orlando Speed World, one of his crew members made a mistake. They underinflated the rear tires. Instead of the planned 8 psi, they went to 5. Now, any self-respecting crew chief sees that number on the gauge and immediately reaches for the compressor. You don't make passes at 5 psi. That's dangerously close to the death zone. That's sloppy work that could cost you a car. Shepard looked at the gauge, looked at the track, looked back at the gauge, and staged the car. The pass he made next didn't just change his season. It changed the sport. The car hooked harder than any of them had ever felt. The 60-foot time dropped by nearly a tenth of a second compared to their best previous run. The crew stood at the end of the track trying to process what had just happened. One number. 5 psi instead of 8. A mistake. And they were suddenly faster than they'd ever been. Shepard didn't celebrate. He got methodical. If 5 was better than 8, what about 4.5? What about 4? He began a systematic test program, bleeding pressure in half psi increments, documenting every change with the kind of obsessive record-keeping that Johnson himself would have respected. And at 4 psi, he found it. The number that would rewrite the rulebook. The contact patch grew by an estimated 50%. The tire, instead of sitting on the asphalt like a rigid cylinder, squatted down and spread out, wrapping itself around microscopic surface variations the way a palm pressing into wet clay conforms to every groove and ridge. More rubber on the track. More traction. Quicker 60-foot times. Every single time. The physics, once you understood them, were almost embarrassingly elegant. And that elegance, that simplicity hiding in plain sight while an entire sport looked the other way, is exactly what makes this story one of the most remarkable in motorsport history. So why did it work? And more importantly, why did it work now, in 1983, when it would have been catastrophic just 5 years earlier? Look, this is the part where most people's eyes glaze over because they assume the physics are going to get complicated. They're not. The physics are actually beautiful in their simplicity, and once you understand them, you'll never look at a tire the same way again. Whether it's on a drag car, a road car, or the grocery getter sitting in your driveway right now. Let's start with something called the contact patch. Every tire, regardless of what it's inflated to, touches the ground through a specific area of rubber. That area is your contact patch, and it is the only part of your car that actually connects you to the road surface. Everything else, every horsepower figure, every pound of downforce, every gram of suspension geometry engineering, all of it has to flow through that contact patch to mean anything. If your contact patch is small, inconsistent, or poorly loaded, none of the rest of it matters. You're just spending money to spin tires. Now here's the fundamental relationship that Shepard understood intuitively before the engineers caught up. The softer your tire, the larger your contact patch, up to a point. A completely flat tire has a massive contact patch but zero structural integrity, so it's useless. A rock-hard tire has excellent structural integrity but a tiny contact patch, so you're essentially balancing a car on a strip of rubber the width of a pencil eraser. The optimal point, the sweet spot, is somewhere between those two extremes. And in 1983, the entire pro stock community had collectively agreed, wrongly, that 8 to 10 PSI was that sweet spot. Shepard found the real sweet spot was half of what everyone believed. Here's why. When a drag slick launches from a standing start, it doesn't simply roll forward. What actually happens is far more interesting and far more violent. The tire wrinkles, the sidewall compresses under the torque load, the tread buckles and folds against itself, creating what racers call the wrinkle wall effect. For a fraction of a second, the tire is doing something that looks, at high speed, like it's turning partially inside out. The rubber literally ripples backward before snapping forward again. This wrinkling action is not a problem. It's a feature. It's the tire's way of absorbing the initial shock of a 500 cubic inch engine hitting the clutch at 7,000 RPM without simply spinning loose and sending the car sideways. Think about it this way. Imagine you're trying to push a basketball and a partially deflated beach ball across a rough surface using a sudden, powerful shove. The basketball, rigid and pressurized, bounces back from the surface immediately. The moment you apply force, it rebounds rather than gripping. The beach ball, soft and compliant, deforms against the surface. It spreads out. It finds grip. It transfers your energy into forward motion rather than upward bounce. That's exactly what's happening between a drag slick and the track surface at launch. Rigidity causes bounce and wheel spin. Compliance causes grip and forward momentum. At 8 psi, the tire is relatively rigid. It wrinkles, yes, but only so much before the internal pressure resists further deformation. At 4 psi, the tire becomes dramatically more compliant. It can absorb more of that initial torque spike, wrap more aggressively around surface imperfections, and maintain contact with the track through a much wider range of motion. The result is a contact patch that isn't just bigger, it's more consistent. Instead of the tire bouncing in and out of contact with the asphalt during those critical first 60 feet, it stays planted through more of the launch cycle. But here's the critical question that nobody has answered yet. If this is so straightforward, if the physics are this obvious, why wasn't everyone already doing it? Why did it take until 1983 for someone to discover that lower pressure meant more traction? The answer has two parts, and both of them matter. First, the tires themselves. The bias-ply drag slicks that dominated through the 1970s had a fundamental structural weakness at the bead, the reinforced edge where the tire locks onto the wheel rim. These older tires needed internal pressure to maintain bead seat. Drop below a certain threshold, somewhere in the 6 PSI range, and the bead would unseat under the lateral forces of a hard launch. When a tire bead unseats at speed, the result is catastrophic and immediate. The tire comes off the rim, the wheel digs into the track, and the car becomes an unguided projectile. Multiple crashes in the late 70s had been traced to bead failures at low pressure, and the institutional trauma from those incidents had calcified into the 6 psi minimum rule that everyone accepted as physics rather than recognizing it as a limitation of a specific tire technology. By 1982, however, Goodyear and M&H Racemaster had introduced a new generation of radial drag slicks with dramatically improved bead construction. The engineering advances in the bead area meant these new tires could maintain a positive bead seat at pressures that would have been suicidal on their predecessors. The floor had dropped. The technology had evolved. But the rules of thumb in the paddock hadn't caught up, because nobody had tested the new tires at the pressures the old tires couldn't survive. The assumption carried forward unchanged, despite the fact that the fundamental limitation driving that assumption no longer existed. This is where it gets really interesting, because the second part of the answer involves a piece of equipment that most teams in 1982 considered unnecessary added weight: bead locks. A bead lock is a mechanical device, essentially a clamping ring that physically bolts the tire bead to the wheel, independent of tire pressure. With a bead lock installed correctly, the tire literally cannot unseat from the rim regardless of internal pressure, because it's mechanically captured rather than relying on air pressure to hold position. NH Pro Stock had legalized bead locks in 1982, and most teams had adopted them as a precautionary measure against the occasional flat tire in the burnout box or during staging. Standard practice, minor convenience, nothing revolutionary. Shepard saw them as the key to an entirely different strategy. With proper bead locks installed and torqued to his crew's exacting specification, 18 foot-pounds in a precise star pattern to ensure even clamping force around the entire circumference, the physical limitation that had made low pressure dangerous simply ceased to exist. The tire could not unseat. It didn't matter what the internal pressure was. The mechanical connection between tire and wheel was independent of air pressure. Shepard could run 3 psi, 2 psi, theoretically 1 psi, and the tire would stay on the rim because steel bolts were holding it there, not air. 4 psi became the number because it was the point where contact patch maximization and sidewall stability reached their optimal intersection. Lower than 4 and the tire would fold so dramatically at launch that the sidewall would actually contact the track surface, creating unpredictable handling and excessive heat buildup in the wrong places. Higher than 4 and you were leaving contact patch on the table. 4 psi on those specific tires with those specific bead locks on those specific tracks was the number. His preparation process was extraordinary in its precision. The tires were mounted at normal pressure first, ensuring proper bead seating before the locks were installed. Then the bead locks were torqued and the pressure was bled down using a gauge that Shepard's crew had sent to a metrology laboratory for calibration, accurate to within half a psi. Not approximately 4. Not somewhere around 4. 4 psi measured against a laboratory standard. In the pits, the tires looked almost flat. Other teams walking past Shepard's area would do double takes, wondering which tire had gone down and why nobody seemed concerned about it. Nobody was concerned because the flat appearance was the whole point. Now, you might be thinking, okay, but surely other teams noticed this. Surely someone saw those Saga tires and put 2 and 2 together pretty quickly. And yes, eventually they did. But here's what people underestimate about the speed of information transfer in a pre-internet, pre-social media racing paddock. Teams were intensely secretive. Setup information was guarded like military intelligence. You didn't walk up to a competitor's car and measure their tire pressure. You didn't share data. You watched, you guessed, and you worked with what you had. What other teams saw was a Camaro with tires that looked wrong, posting times that seemed impossible, passing technical inspection with 0 violations. The logical conclusion most of them reached was that Shepard had found something in the engine, or the clutch, or the chassis. Nobody looked at those flat-looking tires and thought, that's the advantage. They looked at those tires and thought that poor guy has a leak somewhere and doesn't know it. The psychological dimension of this cannot be overstated. Shepard's tires got inside other racers' heads in ways that conventional competitive advantages simply don't. When you line up against someone and their car looks like something is broken, you're distracted. You're spending mental bandwidth trying to figure out what they're hiding instead of focusing on your own race. Meanwhile, Shepard would hit the tree 0.02 of a second ahead, plant those saggy tires into the asphalt, and be 3 car lengths up the track before the other driver finished processing what just happened. At the 1983 Winter Nationals, it wasn't a close competition. It was a statement. Shepard's 60-foot times were consistently 2 to 0.03 quicker than the next fastest car in the field. In pro stock terms, that's not a margin. That's a chasm. Bob Glidden, who had won the NH Pro Stock Championship multiple times and was widely considered the most complete racer in the class, walked to the line in the final, saw Shepard's tires, shook his head, and lost anyway. His car was immaculate. His engine was perfect. His reaction time was excellent. And he got walked because of air pressure. 4 PSI. The number that changed everything. And they were only just getting started. Warren Johnson figured it out first. Of course he did. The professor, as the entire paddock called him, didn't earn that nickname by accepting things at face value. While every other crew chief was still scratching their heads, still pulling apart their engine combinations looking for the horsepower they assumed Shepard had found somewhere in his cylinder heads or his fuel system, Johnson went back to his data. He had rudimentary data acquisition on his car before almost anyone else in pro stock, basic accelerometers and timing sensors that gave him a picture of what was happening during a run that most teams simply didn't have access to. And his data told him something that made everything else suddenly, uncomfortably clear. Shepard's engine wasn't making more power. Johnson could see that in the top end numbers, in the trap speeds, in the elapsed time comparisons between different sections of the track. The power output was comparable. What was different, dramatically, undeniably different, was what was happening in the first 60 feet. Shepard's car was putting power down at a rate that shouldn't have been physically possible given what everyone knew about tire technology. The acceleration curve in those first 60 feet was smoother, more progressive, more complete than anything Johnson's sensors had recorded from any other car in the field, including his own. Johnson didn't need a diagram. He walked over to Shepard's pit area during a break in qualifying, looked at those saggy rear tires, and felt the bottom drop out of his stomach, because he understood immediately. Not just what Shepard was doing, but why it worked, and more devastatingly, why it had taken this long for anyone to try it. He went back to his own pit, told his crew to bleed the rear tires down to 5 PSI for the next session, watched their faces cycle through confusion and concern, and said do it anyway. The improvement was immediate. Not as dramatic as Shepard's, because Johnson was starting from 5 rather than 4 and didn't yet have the bead lock setup optimized for low-pressure operation, but the direction was unmistakable. Lower pressure, more traction, better 60-foot times. The physics didn't lie. Johnson spent the rest of that event methodically working his way down toward 4 PSI, treating the process with the same systematic rigor he applied to every other variable in his operation. By the end of the 1983 season, Warren Johnson had largely closed the gap to Shepard through sheer analytical horsepower. But here's what that story actually illustrates, and it's more important than the tire pressure number itself. Shepard had a full season's head start on optimization. While Johnson was discovering that 4 PSI was better than 8, Shepard was already 3 steps ahead, working on what 4 PSI made possible rather than just what it was. He wasn't standing still waiting for the field to catch up. He was using the advantage he'd built to develop the next layer of innovation, and the layer after that. This is the pattern of genuine innovation in motorsport. The breakthrough itself is only the beginning. The real separation comes from understanding the cascading implications of that breakthrough faster and more completely than anyone else. Shepard understood something that most racers miss entirely. A change this fundamental doesn't just affect one variable. It reshapes the entire performance equation. Every other setup parameter that had been optimized around 8 PSI was now potentially wrong. Not slightly suboptimal. Fundamentally wrong, because the baseline assumption underneath all of it had changed. Take rear-end gear ratio. In 1983, the standard Pro Stock rear-end ratio ran somewhere between 5.13 and 5.29 gears. These steep ratios existed to multiply engine torque at launch, compensating for the fact that the tires were relatively rigid and needed that extra mechanical advantage to get the car moving without breaking traction. It was a solution to a traction problem. Steep gears plus high-pressure tires equaled controllable launches. The math worked. But at 4 PSI, the traction problem was dramatically reduced. The tire was doing so much more work at launch, absorbing and transferring power so much more efficiently, that the steep gear ratio was now actually a liability. Too much torque multiplication into a tire that was already gripping aggressively created a different kind of problem. The car would load up too quickly, the suspension would compress too violently, and the launch would become inconsistent in a new and different way. The solution to the old problem was now causing a new problem. Shepard's answer was to run taller gears. While the field was still bolting in 5.13 ratios, he moved to 4.88. The taller ratio meant his engine didn't have to rev as aggressively at launch. It meant less mechanical stress on the ring and pinion, less heat generated in the rear end, and crucially, more consistent power delivery through the early part of the run. The engine stayed in a narrower, more controllable RPM range through the launch sequence rather than spiking wildly as the clutch engaged. The downstream effects were remarkable. Transmissions lasted longer because the shock loads at each gear change were reduced. Clutch wear became more predictable, which meant the clutch could be tuned more precisely because you could actually forecast its behavior rather than just reacting to it. Valve train components survived more runs between rebuilds because the engine wasn't being asked to rev to its absolute limit from a dead stop on every single pass. The cost per run dropped. The consistency per run increased. One innovation, 4 PSI, had cascaded into improvements across the entire drivetrain. Here's what most people don't realize about this period in pro stock history. The teams with the biggest budgets were actually at a disadvantage in adapting to Shepard's innovation. Not because they lacked the resources to test it, but because they had more infrastructure built around the old assumptions. Glidden's Ford program had specific gear sets, specific clutch packages, specific engine tuning maps that had been developed and refined over years of competition at 8 to 10 psi. Switching to 4 psi didn't just mean adjusting the tire pressure. It meant questioning and potentially discarding years of accumulated setup knowledge. That's psychologically and organizationally difficult, even when the data is staring you in the face. Shepard's smaller operation was actually more agile. He had less legacy infrastructure to dismantle. He could change the gear ratio on Tuesday, test it Wednesday, evaluate the data Thursday, and race with it Friday. Larger teams had approval processes, had suppliers who needed lead time, had crew members who'd built their expertise around specific ways of doing things and needed time to adapt. The organizational flexibility of a leaner operation turned out to be a genuine competitive asset during a period of rapid technical change. The track surface itself became a new variable that Shepard was exploiting in ways nobody else had considered. Most racers in this era treated the track as a fixed condition, something you adapted to rather than something you actively managed against. You went to a race, you assessed the track, You set your car up as best you could for whatever conditions existed, and you hoped for the best. Shepard started thinking about the interaction between his tire pressure and the specific track surface in a much more dynamic way. Different tracks had different asphalt compositions, different aggregate sizes in the surface, different levels of rubber buildup in the groove, different drainage characteristics that affected surface temperature. All of these variables affected how a tire at 4 psi would interact with the track compared to a tire at 8 psi. Shepard started building what amounted to a database of track-specific pressure adjustments. Not just 4 psi everywhere, but 4 psi as the baseline with documented modifications for specific venues and specific conditions. At a track with a coarser aggregate surface, the tire at 4 psi would interlock with the surface texture more aggressively, potentially giving too much traction too quickly and causing the chassis to pitch forward in a way that actually hurt the 60-foot time. The answer might be 4.3 psi, enough to soften the initial bite slightly and let the car load more progressively. At a track with heavy rubber buildup in the groove, the surface was already sticky, so the tire at 4 psi might actually generate more heat than the compound could efficiently dissipate. The answer might be 4.5 psi to reduce the flex cycle slightly and manage tire temperature. These adjustments sound tiny. They are tiny. They are also the difference between winning and losing in a class decided by thousandths of a second. The crew member Shepard designated as his tire pressure specialist became arguably the most important person in the operation aside from Shepard himself. This person carried the calibrated gauge at all times. They monitored ambient temperature between rounds, cross-referenced it against the adjustment charts Shepard had developed through testing, and recommended pressure changes that might be as small as 1/10 of a psi. They took tire temperatures with an infrared gun after every run, mapping the heat distribution across the tread face and comparing it against the target pattern that Shepard had determined indicated optimal contact through the run. Modern teams take this kind of data-driven approach completely for granted. In 1983, it was genuinely revolutionary. Shepard was doing sports science before sports science was a phrase anyone used in a racing context. He was treating tire management as a precision discipline with measurable inputs and quantifiable outputs rather than as black magic practiced by experienced crew chiefs operating on gut feel and superstition. And the results bore out the approach. Through the 1983 season, Shepard's 60-foot times showed a standard deviation that was roughly half that of his nearest competitors. It wasn't just that he was faster. He was faster and more consistent. In drag racing, consistency is often more valuable than raw speed, because an inconsistent car forces you into reactive driving, adjusting your technique run to compensate for varying behavior. A consistent car lets you drive the same way every time, which means your reaction times improve, your shift points optimize, and your overall package becomes more than the sum of its parts. By the time the 1983 season reached its midpoint, the secret was effectively out. Teams had noticed. Some had experimented. A few had made meaningful progress toward replicating Shepard's low-pressure setup. But replicating the number was the easy part. Understanding the system around the number, the gear ratios, the clutch tuning, the track-specific adjustments, the tire temperature management, the suspension settings that had been recalibrated to work with a softer tire contact patch rather than a rigid one, that was the intellectual property that Shepard had built over months of systematic testing and that nobody else could simply copy by looking at his tires in the staging lane. This is where it gets really interesting, because the tire companies themselves were now paying attention in a way that would change the direction of product development for the next decade. Goodyear sent a team of engineers to observe Shepard's operation. What they found challenged some of their fundamental assumptions about how their own product worked. At 4 psi, their tires were operating in a performance envelope that their design process had never targeted. The contact patch geometry was different from what their models predicted. The heat distribution through the carcass was different. The wear patterns were different. The tires were doing things at 4 PSI that Goodyear's engineers hadn't designed them to do, and yet they were doing those things faster and more consistently than anything the engineers had designed for. The logical response was not to tell Shepard he was wrong. The logical response was to go back to the drawing board and start designing tires that were optimized for the performance envelope he'd discovered rather than the one they'd assumed was correct. And that decision, made in a series of engineering meetings at Goodyear's Akron headquarters during the winter of 1983 and 1984, would produce the next generation of drag slicks that made 4 PSI not just a viable operating condition but the intended operating condition. Tires engineered from the ground up to perform at pressures that the previous generation couldn't survive. The sport was changing, and Lee Shepard was the one changing it. The 1984 Summer Nationals at Englishtown, New Jersey. 95 degrees. Humidity so thick you could wring it out of the air like a wet towel. The track surface was greasy, unpredictable, the kind of conditions that made crew chiefs age visibly between rounds. Cars that had been hooking perfectly in the cool morning air were spinning through the lights by mid-afternoon. Teams were scrambling, pulling gear ratios, adjusting clutch timing, throwing setup changes at the wall and hoping something would stick. Shepard's crew was calm. While every other pit area looked like a controlled emergency, Shepard's team was working through their standard pre-round checklist with the methodical quiet of people who had a plan and trusted it completely. The tire pressure specialist checked the ambient temperature, checked the track surface temperature with an infrared gun, consulted the adjustment chart, made a recommendation. Shepard listened, nodded, and told his crew to bleed the rear tires to 3.8 psi. Not 4. 3.8. His crew had never gone that low in competition. Testing, yes. Race day, never. A couple of them exchanged glances. The tires, when they hit that number, looked genuinely alarming. Not like race car tires. Like something had gone badly wrong in the paddock and nobody had noticed yet. Other teams walking the pit lane were stopping, staring, pointing. Whispers moved through the staging area. Shepard's got a flat. Something's wrong with the Camaro. He's never going to make it through the burnout. Shepard staged the car, hit the trans brake, and waited for the tree. First qualifying pass. 7 seconds, 38 hundredths at 181 miles per hour. The field average at that point in the session was 7:55. Shepard had just put nearly 2 car lengths on the entire field in a single qualifying run on the worst track conditions of the season. Bob Glidden walked to the timing board, read the number, walked to Shepard's pit area, looked at those 3.8 psi tires without saying a word, turned around and walked back. His crew chief would later say it was the only time he'd ever seen Glidden look genuinely defeated before eliminations had even started. But here's what made that run even more remarkable than the number itself. The track was terrible for everyone else. For Shepard, the terrible track was actually an opportunity. Here's what most people don't realize about the relationship between track conditions and tire pressure at the extreme low end of the pressure range. In hot, greasy conditions, a tire at standard pressure becomes less effective because the heat reduces the compound's ability to generate chemical adhesion with the track surface. The tire gets shiny, loses its bite, and starts skating rather than gripping. At 3.8 psi, something different was happening. The increased sidewall flex was generating more internal heat in the tire carcass, which was keeping the compound in its optimal operating temperature window even as the external track temperature was pushing conventional setups out of their range. The tire was essentially self-regulating its compound temperature through the mechanical energy of flex, maintaining grip in conditions where higher pressure tires were cooking themselves into uselessness. Shepard hadn't just found a setup that worked in good conditions. He'd found one that actually worked better in bad conditions than the alternative. This is the hallmark of a truly fundamental innovation as opposed to an incremental improvement. Incremental improvements make things better when everything is already working well. Fundamental innovations change the performance equation in ways that create advantages precisely when conditions are most challenging. 4 psi and its close relative 3.8 psi was a fundamental innovation. The elimination rounds that weekend were almost anticlimactic. Shepard ran consistent 7.40s while the rest of the field struggled to get into the low 7.50s on the difficult track surface. In the semi-final he faced Wally Booth, who had done an admirable job of managing the conditions and was genuinely quick. Shepard's 60-foot time was 0.908. Booth's was 0.951. The race was over in the first second and a half. Booth drove a perfect run and still lost by 4.5 car lengths. The final paired Shepard against Warren Johnson, who by this point had been running low pressure for several months and had genuinely closed a significant portion of the gap. Johnson was at 4 psi, properly optimized, with beadlocks correctly torqued and a gear ratio he'd adjusted based on his own testing data. He was the only person in the field who had a legitimate theoretical chance of beating Shepard on this day. Johnson's 60-foot time was 0.943 seconds. Excellent. Among the best numbers he'd run all season. Under normal circumstances, against any other car in the field, that would have been more than enough. Shepard's 60-foot time was 0.908 seconds. 35 thousandth. In a class where 10 thousandths separated first and fifth in qualifying, 35 thousandths at 60 feet was a margin so large it was almost embarrassing to discuss in polite company. That gap, built in the first 60 feet of a quarter-mile run, translated to a comfortable half-car-length victory at the finish line despite Johnson driving a nearly perfect race from 60 feet onward. Shepard's elapsed time was 7.382. Johnson's was 7.401. The margin of victory in elapsed time was 19 thousandths of a second. Shepard had built a margin of 35 thousandths in the first 60 feet and then given back 16 thousandths over the remaining 1,260 feet because at that point, both cars were essentially equal. The entire race was decided in the first 60 feet. By tire pressure. Now you might be thinking, okay, Johnson figured it out, he was at 4 psi, so why was Shepard still faster? This is where the depth of Shepard's advantage becomes really clear. The number 4 psi was the beginning of the knowledge, not the end of it. Johnson had the number. Shepard had the system. He had months of data on how that specific tire, at that specific pressure, interacted with his specific suspension geometry, his specific clutch engagement rate, his specific gear ratio, his specific driving technique. He had a mental model of his car's behavior at 4 psi that was so refined, so detailed, that he could feel deviations from the optimal launch sequence and make micro-corrections in real time. Johnson was still learning. Shepard was performing. The difference between those two states, learning and performing, is the difference between understanding a concept intellectually and having it so deeply integrated into your practice that you execute it without conscious effort. Johnson knew 4 psi was right. Shepard knew, in a different and deeper way, exactly how 4 psi felt when everything was working perfectly, and exactly what to do when it didn't. That kind of knowledge doesn't transfer through observation. It only comes from thousands of repetitions and the willingness to analyze each one honestly. The tire companies were now in a full development race of their own, driven entirely by what Shepard had revealed about the performance possibilities at ultra-low pressure. Goodyear's engineering team had gone back to their design process and started asking different questions. Instead of designing a tire that was stable and predictable at 8 to 10 psi, they began designing one that was stable and predictable at 3 to 5 psi. The structural requirements were completely different. At low pressure, the sidewall needed to flex in controlled, predictable ways rather than resist flexing. The bead area needed to be exceptionally strong not to maintain air seal, because bead locks handled that, but to survive the mechanical stresses of repeated severe flex cycles without fatiguing and cracking. The compound development was equally involved. At 4 psi, the tire was generating significantly more internal heat through the flex cycle than at 8 psi. Conventional compounds would overheat, blister, and lose grip rapidly. Goodyear began working on compounds with higher thermal stability that could maintain their grip characteristics across a wider temperature range. They also started exploring directional tread patterns, asymmetric compound distributions, and variable thickness sidewall designs that would promote the right kind of flexing at launch while providing enough recovery stiffness to prevent the tire from folding completely under extreme conditions. M&H Racemaster took a different approach that was arguably more elegant. Rather than trying to make a compound that was thermally stable at the higher temperatures generated by low-pressure flex, they engineered one that actually got stickier as it heated up within the operating range that 4 psi created. The compound's grip characteristics were intentionally temperature-dependent in a positive direction. The more the tire flexed, the hotter it got, the stickier it became, turning what had been considered a liability, heat generation from excessive flex, into a self-reinforcing performance advantage. This development work, triggered entirely by Shepard's willingness to run 4 psi when everyone said 6 was the floor, produced a generation of drag racing tires that made the entire pro stock class dramatically faster. When you see modern pro stock cars running in the mid-6-second range at over 215 miles per hour, you are looking at a performance level built on a foundation that Lee Shepard laid with a bleeder valve and a calibrated pressure gauge in 1983. The psychological warfare dimension of Shepard's advantage evolved as the season progressed and his dominance became undeniable. In the early part of the year, other teams were confused and distracted by the unexplained performance gap. By mid-season, when the low-pressure secret was widely understood, a new psychological dynamic took over. Shepard became the standard against which everyone measured themselves, and that kind of status creates its own pressure on the competition in ways that are subtle but genuinely performance-affecting. When you are racing for second place and you know it, your decision-making changes. You start taking risks you wouldn't otherwise take, making setup gambles that your data doesn't fully support, because conservative, data-driven decisions will produce second place, and you need something different to win. Those gambles occasionally pay off spectacularly and more often blow up in your face, creating inconsistency that compounds the original performance deficit. Teams that were already slightly behind Shepard on pure pace were making themselves worse through the desperation his dominance inspired. Shepard, meanwhile, was racing against the clock and his own previous best rather than against the field. When you're the benchmark, you don't need to take risk. You execute your process, run your numbers, and let the competition exhaust themselves trying to catch something they don't fully understand. The mental game in pro stock is enormous, and Shepard was winning it as completely as he was winning the physical race. The 1984 championship came down to the final race of the season. Shepard needed a semi-final appearance to clinch regardless of what anyone else did. He made the semis, lost on a hole shot to a racer who caught him napping on the tree, and still won the championship by a margin that would have been considered comfortable in any other era. His 60-foot average for the season, compiled across every qualifying session and elimination round, was 0.916 seconds. The field average was 0.951. 35 thousandths consistently all season long. Not a fluke. Not a lucky track condition. A systematic, repeatable advantage built on one fundamental insight and months of meticulous optimization. Here's what most people don't realize about what happened next. NHRA's response to Shepard's dominance was not to ban low tire pressure, because there was nothing inherently unsafe about it with proper bead locks installed and modern tire technology. Instead, they did something that revealed exactly how much the sport had been changed. They tried to regulate it. In early 1985, they proposed a minimum tire pressure rule of 7 psi, essentially trying to wind the clock back to where conventional wisdom had been before Shepard started bleeding air out of his tires. The rule lasted one race weekend before teams found workarounds so creative, so immediately obvious once you understood the underlying physics, that the governing body had no choice but to abandon the attempt. Teams filled their tires with helium instead of air, exploiting the fact that the rule specified pressure in PSI without specifying the inflation medium. Helium molecules are smaller and lighter than nitrogen or oxygen molecules, producing different density characteristics at the same measured pressure. It was technically compliant, practically absurd, and immediately obvious to anyone with a basic understanding of gas physics. The rule was rescinded. 4 psi became not just accepted practice but standard operating procedure. And Shepard, who had spent 2 years being the only person in the sport running a setup that looked wrong to everyone watching, was now the person everyone was trying to copy. He had one more season of development to share with the sport before tragedy intervened. And what he was working on in early 1985 made everything that had come before look like the opening chapter of a much longer story. The winter of 1984 into 1985 was the most productive testing period of Lee Shepard's career. And that's saying something, because the previous 2 years had produced innovations that restructured an entire racing class. But Shepard wasn't satisfied. He never was. The 4 psi revolution had given him 2 championships and a level of dominance that most racers never experience in an entire career. For Shepard, it was a starting point that kept revealing new directions the deeper he pushed into it. Here's the thing about genuine innovators. They don't see a solved problem and move on. They see a solved problem and immediately start asking what the solution reveals about the next problem. Shepard had spent 2 seasons learning things about tire behavior at ultra-low pressure that nobody else in the sport knew, because nobody else had accumulated the same volume of carefully documented test data at those conditions. And that data was showing him things that went well beyond simply running 4 psi and going faster. The first new frontier he was exploring was tire stagger. In oval racing, stagger is a well-established concept. You run different diameter tires on the left and right sides of the car to help it turn through corners by exploiting the difference in rolling circumference. In drag racing, which runs in a straight line, stagger had always been considered irrelevant at best and counterproductive at worst. Why would you run different diameter tires side to side on a car that only needs to go straight? Because drag strips are not perfectly straight. And more importantly, they are not perfectly level. Every drag strip in America is built with a slight crown, a gradual rise from the outside edges toward the center, designed to allow rainwater to drain off the racing surface rather than pooling and creating hazards. This crown is subtle, typically only a fraction of an inch across the full width of the track, but at the launch forces generated by a pro stock car, subtle asymmetries in the track surface create measurable asymmetries in tire loading. The tire on the high side of the crown is carrying slightly less weight than the tire on the low side. It's generating slightly less traction. And at 4 psi, where the tire is so sensitive to loading conditions that a tenth of a psi change in pressure produces measurable performance differences, slightly less traction on one side creates a steering tendency that the driver has to correct with steering input. Steering input at launch, even tiny, unconscious corrections, bleeds energy away from forward momentum. The front tires are being asked to do 2 jobs simultaneously, supporting the front of the car and correcting the car's path, instead of just one job. The result is a launch that's slightly less efficient than it would be on a perfectly level surface with perfectly equal loading on both rear tires. Shepard's solution was elegant. By running a 1/4 psi less pressure on the low side rear tire, he could increase that tire's contact patch slightly, equalizing the effective traction between left and right rear and eliminating the need for steering correction at launch. The car tracked straight not because the driver was holding it straight, but because the setup was balanced against the specific asymmetry of the track surface. This freed the driver, which was Shepard himself, to focus entirely on reaction time and shift points rather than dividing attention between driving straight and going fast. The pressure difference required varied by track. Some strips had more crown than others. Some had repaving on one side that changed the surface texture asymmetrically. Shepard's database grew to include not just temperature-based pressure adjustments but track geometry-based adjustments, specific to each venue on the NH schedule. This was the kind of granular, venue-specific knowledge that takes years to accumulate and cannot be replicated simply by knowing the concept exists. The second frontier he was exploring was inflation medium. Air, the standard inflation gas for every tire in every form of motorsport, is a mixture of roughly 78% nitrogen, 21% oxygen, and small amounts of other gases. The oxygen component is chemically reactive. It reacts with the rubber compounds in the tire, contributing to oxidative degradation over time. More relevantly for short-term performance, oxygen molecules are smaller and more energetic than nitrogen molecules, which means air-inflated tires change pressure more rapidly with temperature changes than nitrogen-inflated tires do. In a sport where Shepard was managing pressure to within 1/10 of a PSI and where track temperature could swing 20 degrees between a morning qualifying session and an afternoon elimination round, pressure consistency was enormously valuable. A tire inflated with air at 4 psi in 60-degree morning temperatures might be at 4.3 psi by the time afternoon eliminations rolled around in 80-degree heat. That 0.3 of a psi change, invisible to anyone not using a precision gauge, was enough to measurably affect the contact patch size and alter the launch characteristics in ways that required compensating adjustments. Nitrogen inflation offered a significant improvement. Because nitrogen molecules are larger and less reactive than oxygen, nitrogen-inflated tires are dramatically more stable across temperature changes. A tire at 4 psi with nitrogen in the morning would be at 4.05 psi in the afternoon, rather than 4.3. The pressure stayed where you put it. The contact patch stayed consistent. The launch behavior stayed predictable. For a team built around precision and consistency, the switch to nitrogen was not optional. It was mandatory. Shepard had been running nitrogen in his tires since mid-1984, quietly, without announcing it, while teams that had copied his 4 psi pressure setting were still using air and wondering why their pressure management was less consistent than his. This was another layer of the system that the number alone didn't reveal. You could know 4 psi was the target and still not achieve what Shepard achieved, because without nitrogen and without the precision gauge and without the temperature adjustment charts and without the track geometry database, 4 psi was just a number. In Shepard's hands, it was a precisely calibrated, dynamically managed, venue-specific system that happened to be centered around 4 psi. The third area of development in that winter of 1984 to 1985 involved infrared temperature mapping of the tire surface during and after runs. Shepard's crew had begun using military surplus infrared imaging equipment, the kind originally developed for battlefield target acquisition, to create detailed temperature maps of the tire tread surface immediately after each run. These maps revealed information about the contact patch that no other measurement technique could provide. A perfectly working tire at 4 psi, making optimal contact with the track surface throughout the launch, would show a specific heat distribution pattern across the tread face. The center of the tread would be slightly hotter than the edges, reflecting the higher pressure concentration in the middle of the contact patch. The temperature would be highest in the section of the tire that corresponded to the most aggressive part of the launch, the point where the tire was transitioning from static to dynamic loading, and would taper off toward the edges of where the contact patch had been. Deviations from this ideal pattern told Shepard's crew specific things about what was going wrong and why. A tire that ran too hot on the inside edge indicated excessive negative camber, meaning the suspension geometry was loading the inside of the contact patch too aggressively. A tire that showed uneven temperature distribution front to back across the tread indicated that the tire was spinning slightly during part of the launch, creating frictional heat unevenly rather than the consistent thermal signature of a tire that had hooked cleanly from the very first instant of launch. These temperature maps became a diagnostic language. Shepard's crew could read a post-run tire map the way a doctor reads a medical scan, identifying specific mechanical issues from the thermal evidence left in the rubber. A chassis problem that would have taken hours of test passes to diagnose through lap time analysis could be identified in minutes by reading the tire temperature map from a single run. This compressed the test cycle dramatically, allowing Shepard's team to make more meaningful setup changes per test day than any competitor. The tire companies were watching all of this with intense interest. Goodyear's engineers had become effectively embedded in Shepard's operation by early 1985, observing testing sessions, collecting data, and feeding information back to their development program. The relationship was mutually beneficial. Shepard got access to pre-production tire compounds and construction variations that weren't available to other teams. Goodyear got real-world performance data from the sport's most advanced tire management operation. The tires being developed in that collaboration were not incremental improvements on existing product. They were fundamentally different designs built around the operating conditions that Shepard had defined. One development from that collaboration deserves specific attention because of how far ahead of its time it was. Goodyear's engineers, working from Shepard's infrared temperature data, identified that the optimal contact patch at 4 PSI was not the oval shape that conventional tire design produced. At ultra-low pressure, the tire naturally wanted to form a more rectangular contact patch, with more consistent pressure distribution across the full width of the tread rather than the concentrated center loading of a higher-pressure oval patch. But the conventional symmetric tread design was fighting this natural tendency, creating inconsistencies in the contact patch shape that showed up as irregular temperature distributions in Shepard's infrared map. The solution was an asymmetric tread design, with different tread block sizes and spacings on the inside and outside edges of the tire, calibrated to produce a more consistently rectangular contact patch at 4 psi operating pressure. This design wouldn't be ready for competition until mid-1985, but preliminary testing in the winter showed contact patch improvements that translated to another 2 to 3 thousandths of a second in 60-foot times. Tiny numbers. Enormous significance. Now, you might be thinking, this sounds like it's getting into diminishing returns territory. How much faster can you go by optimizing tire pressure and contact patch shape? And this is exactly the right question because it gets at something fundamental about how innovation works in motorsport. Individual innovations do hit diminishing returns, but they also enable other innovations that have their own improvement curve. The significance of Shepard's work was not just what it contributed directly to lap times. It was what it made possible for everyone who came after. Consider the modern pro stock car. Today's machines run tire pressures as low as 3.5 psi on purpose-built bead lock wheels with multi-piece designs that allow the tire bead to be mechanically secured with a precision that makes Shepard's 1983 bead locks look crude by comparison. The tires themselves are engineered with finite element analysis of the sidewall flex behavior at operating pressure, optimized for the exact flex characteristics that generate maximum contact patch without inducing the kind of irregular deformation that creates handling issues. The inflation medium is nitrogen, dried and filtered to a specific purity standard. The pressure monitoring is electronic, continuous, and accurate to hundredths of a psi. All of this exists because Lee Shepard asked what happens if we go lower, and then spent 2 years building the knowledge system around the answer. The human cost of this story arrives in the spring of 1985, and it is impossible to discuss the legacy of Lee Shepard without confronting it directly. On March 30, 1985, during a private test session at Ardmore Dragway in Virginia, Shepard's Camaro experienced a catastrophic mechanical failure at speed. The details of exactly what failed and why have never been fully resolved, but the outcome was not in doubt. The car left the racing surface at high speed, and Lee Shepard, four-time NH Pro Stock champion and the most innovative mind the class had ever produced, died at the scene. He was 41 years old. The racing community's response was immediate and genuine. These were competitors who had spent 2 years being beaten by Shepard, frustrated by his advantages, working nights and weekends trying to close gaps he kept widening. And to a person, they mourned him. Not just as a competitor, but as someone who had made the sport better, harder, more demanding, more intellectually rigorous. Bob Glidden, who had perhaps lost more to Shepard's innovations than anyone else in the field, said publicly that Shepard had forced him to become a better racer by raising the standard of what was possible. Warren Johnson, characteristically, expressed his grief in technical terms. He said that Shepard's death had cost the sport 10 years of development, because wherever Shepard's curiosity was pointing next, the rest of the field would have eventually followed, and the journey would have been shorter with Shepard leading it. Coming from the professor, that was both a profound compliment and a precise technical assessment. Johnson understood better than most exactly how far ahead of the field Shepard's thinking had been, because he was the one who had come closest to catching up. The innovations didn't die with Shepard. They couldn't. They were already embedded in the sport, in the tire designs, in the bead lock specifications, in the gear ratio choices, in the pressure management protocols that every pro stock team had adopted. 4 PSI was the standard now. The asymmetric tread designs were in production. The nitrogen inflation practice was spreading. The infrared temperature mapping techniques were being replicated. Shepard's intellectual legacy was distributed across the entire field, carried forward by the competitors he had spent 2 seasons teaching through the instrument of competition. This is where it gets really interesting from a historical perspective, because Shepard's story illustrates something about innovation that goes beyond motorsport. The most valuable innovations are not always the ones that are most protected and proprietary. Sometimes the most valuable thing an innovator can do is demonstrate so completely and publicly that something works that the entire field adopts it, raising the baseline for everyone and creating conditions where the next generation of innovation becomes possible. Shepard didn't file patents on 4 PSI. He didn't license his tire management system. He raced it openly, won with it publicly, and forced the entire sport to evolve to meet him. The sport that emerged from that process was fundamentally different from the one he'd entered, and the path to the modern pro stock car runs directly through his innovations. So what does a Florida racer with a pressure gauge and an open mind actually leave behind? What is the real, lasting, measurable legacy of Lee Shepard and the 4 PSI revolution? Because I think most people, even serious drag racing fans, significantly underestimate the answer to that question. And I want to spend the final part of this story making sure you leave here understanding exactly how deep those roots go. Start with the numbers, because the numbers are where the truth lives. In 1982, the year before Shepard began his systematic low-pressure testing program, the quickest pro stock 60-foot time recorded at an NH national event was 1.048 seconds. By 1986, just 1 year after Shepard's death and 3 years after his innovation became standard practice, the class record had dropped to 0.898 seconds. That is 15/100ths of a second. In a class where thousandths determine outcomes, 15/100ths is not an improvement. It is a different universe, and the vast majority of that improvement traces directly to tire pressure management rather than engine development, because the engine rules in pro stock changed very little during that period. The tires changed. The pressure changed. Everything else followed. Today's pro stock cars run in the mid-6-second range. The 60-foot times that elite teams are posting in 2024 sit in the 0.860 to 0.875 second window. That continued improvement beyond the initial 4 PSI revolution reflects 4 decades of incremental development built on the foundation Shepard established. Better tire compounds, better bead lock designs, better suspension geometry calibrated for ultra-low pressure operation, better data acquisition revealing finer and finer optimization opportunities. But the foundation is still 4 PSI. The foundation is still the insight that more contact patch beats more pressure every single time, as long as you have the technology to manage the consequences. Here's what most people don't realize about how far Shepard's influence traveled beyond drag racing itself. The principles he demonstrated, that tire compliance at contact produces more consistent grip than tire rigidity, that contact patch shape matters as much as contact patch size, that inflation medium affects pressure consistency across temperature ranges. These are not drag racing specific insights. They are fundamental truths about tire physics that apply everywhere rubber meets road. NASCAR Cup teams began experimenting with lower qualifying pressures in the late 1980s, specifically citing the drag racing data from Shepard's era as the conceptual starting point for their own low-pressure investigations. Formula One engineers, working in a completely different performance context with radically different tire constructions and operating temperatures, nonetheless drew on the contact patch optimization principles that Shepard's work had made undeniable. The idea that you should engineer your tire pressure around maximizing the quality of the contact patch rather than around maintaining structural rigidity became a foundational principle of performance tire engineering across every form of motorsport. Even road car tire development felt the downstream effect. The low-profile, wide-footprint tires that became standard on performance road cars through the 1990s and 2000s reflect a design philosophy directly connected to the contact patch maximization principles that drag racing explored so ruthlessly in the 1980s. You are driving on Shepard's legacy every time you take a corner on a modern performance tire. You just didn't know his name until today. Look, I want to address something directly, because I think it matters for how we understand this story. There is a temptation, when telling the story of an innovator who died young, to romanticize the tragedy and let it overshadow the achievement. To make the story about what was lost rather than what was built. I want to resist that temptation, because I think it does Shepard a disservice. The tragedy is real. 41 years old, 4 championships, a mind still generating ideas that the rest of the sport hadn't caught up to yet. The loss is genuinely painful to contemplate even 40 years later. But the achievement is separate from the tragedy, and it stands completely on its own. Shepard changed his sport. Not incrementally, not marginally, but fundamentally. He identified a limitation that everyone else had accepted as physics and revealed it as assumption. He built a knowledge system around his discovery that was so comprehensive and so rigorously tested that it took the entire field years to replicate even the surface-level version of what he was doing. He forced the tire companies to redesign their products, forced the governing body to rewrite its regulations, forced every crew chief and engineer in pro stock to question things they had considered settled. He did all of this with a bleeder valve, a calibrated pressure gauge, and the willingness to look foolish in the staging lanes while everyone else shook their heads at his saga tires. And here's the thing about that image, Shepard in the staging lanes with those almost flat-looking rear tires, that I keep coming back to. It's the perfect visual metaphor for what genuine innovation actually looks like in practice. It doesn't look like brilliance. It doesn't look like a breakthrough. It looks wrong. It looks like a mistake. It looks like something that experienced, knowledgeable people should immediately correct. The entire field of pro stock, populated by some of the smartest, most technically sophisticated racers in America, looked at Shepard's tires and saw a problem. Shepard looked at his tires and saw a solution. That gap, between what looks wrong to experienced eyes and what actually works when you measure it honestly, is where every important innovation lives. It's uncomfortable territory. It requires a specific kind of courage that is different from physical bravery, though Shepard had that too. It requires the intellectual courage to trust your data over the consensus, to keep pushing in a direction that everyone around you is telling you is dangerous or foolish or both, because your numbers say the direction is right even when your instincts have been trained by years of conventional wisdom pointing the other way. Warren Johnson said it best in a 1986 interview, reflecting on what Shepard had meant to the sport. He said that Shepard had reminded everyone that the most important question in racing is not how do we do this better, but why are we doing it this way at all. That distinction between optimization within existing assumptions and questioning the assumptions themselves is the difference between incremental progress and revolution. Pro stock has had plenty of optimizers, people who took existing approaches and refined them with extraordinary skill and dedication. Bob Glidden was perhaps the greatest optimizer the sport has ever produced. But Shepard was something rarer and more disruptive. He was a questioner, someone who looked at the established order and asked why with genuine curiosity rather than rhetorical posturing, and then went out to the test track and found out. The modern racer who benefits most directly from Shepard's legacy is probably not aware of it. When a pro stock crew chief today runs a tire pressure check between rounds, consulting a digital gauge accurate to hundredths of a PSI and cross-referencing against a temperature-based adjustment protocol, they are executing a process that Shepard developed. When a tire engineer at Goodyear runs a finite element analysis of sidewall flex behavior at 3.5 psi operating pressure, they are working within a performance envelope that Shepard defined. When any racer at any level questions a setup convention that everyone accepts as fact and then actually goes and tests the alternative, they are channeling something essential about how Shepard approached his craft. This is where it gets really interesting as a final thought, because Shepard's story is not just a racing story. It is a story about the mechanism of progress itself, about how knowledge actually advances, not through the orderly accumulation of incremental improvements within established frameworks, but through moments when someone refuses to accept the framework and goes looking for what's on the other side of it. Those moments are uncomfortable for everyone involved. They require the innovator to absorb enormous social pressure to conform, enormous institutional resistance to change, and enormous personal risk of being wrong publicly and expensively. Shepard absorbed all of that. He ran 4 psi when every experienced voice in the paddock said 6 was the minimum. He bled his tires to 3.8 psi on a greasy track in 95-degree heat when his own crew thought he'd lost his mind. He kept pushing, kept testing, kept questioning, right up until the spring morning in Virginia when he didn't come back from a test run. 4 psi. The number that changed drag racing. The number that influenced motorsport engineering for 4 decades. The number that started as a crew member's mistake, became one racer's obsession, and ended up embedded permanently in the DNA of every performance tire developed since. Remember that number next time someone tells you there's a minimum. Remember that the floor is often just the point where the previous generation's technology ran out of capability, not the point where physics runs out of possibility. And remember Lee Shepard, the Florida racer with the Saga tires and the calibrated gauge and the courage to find out what was on the other side of what everyone knew was true. Because motorsport doesn't advance through consensus. It advances through the people willing to look wrong right up until the moment they're proven right. Shepard was proven right by the stopwatch every single time, and the sport has never been the same since. If this kind of deep technical storytelling is what you come here for, you are exactly the person this channel exists for. Hit that subscribe button, drop a comment telling me which part of Shepard's story hit hardest for you, and share this with someone who thinks they already know everything about drag racing. Until next time, keep questioning the floor.